My task today is to explain how to use an effective field theory framework in order to explain how there was potentially a strong first-order electroweak phase transition early on in the universe. And this was work done together with Thomas Tenkanen and Graham White on reconciling thermal resummation with gauge invariance in a unified framework, but also with work by Andreas Ekstedt and Thomas Tenkanen and me, putting forward a software package named DRalgo that really computes and constructs the corresponding effective theories at high temperatures for a plethora of beyond the standard model theories. One of the challenges in cosmology today is to understand what is the thermal history of the universe, and one experiment in order to shed light on that will be LISA, which is a next generation space-based interferometer that will fly in the next 15 years from now. So LISA will eventually shed light on what and how the electroweak symmetry breaking occurred, and if it occurred via a strong first-order phase transition, then it could have left some remnants. Well, some of these remnants are, for example, the baryon symmetry of the universe, and on the other end, there could have been a stochastic gravitational wave background. However, for that, the phase transition should have been strong on first order, and this is not entirely the case in the standard model, which is an old, boring, smooth crossover. We can see this in this plot here, where the mass of the Higgs is plotted on the x-axis, and of course the physical mass is much to the right here. So what happens is that the interpolation between the symmetric phase and the broken phase is just fully smooth crossover, while the mass of the Higgs should have been artificially light in order to hit this first order phase transition. So what one can do is one can extend the standard model with scalars that are light and strong enough coupled to the Higgs so that they actually can change the phase transition thermodynamics and dynamics itself. So what happens now is that there is a lot of effective theories, a lot of beyond the standard model theories that all produce potentially a stochastic gravitational wave background, but if that background is even detectable is one of the major questions. At the same time, if one then chooses a model, one can use some complementarity with colliders, namely future high energy colliders, and then really target, for example, certain masses and parameter space regions in order to constrain or verify if such particles are even existing. So here we can also see that, for example, how such a phase transition occurs. It occurs via the nucleation and expansion of bubbles in the plasma, and the bubbles contain the neutral vacuum, and they expand, they collide, and they source gravitational waves, because such a collision is really such a violent event that eventually distorts space-time itself. Now, we've heard about a large number of beyond the standard model theories that can source a stochastic gravitational wave background. Now, the connection between these theories and the background is through a multitude of different theoretical steps. Each of these steps has their own theoretical uncertainties, which means that they need to be under control. For that, I'll look at one of these parts of the pipeline, namely the connection between the beyond the standard model physics, or Lagrangian, with its equilibrium thermodynamics. And this thermodynamics is encoded in the parameters, namely alpha and beta, which correspond to the strength of the transition, but also the time scale of the transition. So how to get these thermodynamic parameters? And the answer is using the effective potential, which is one of the main characters of this talk. So one needs to understand this effective potential very well, because it encodes, for example, the critical temperature, where the potential has 2 degenerate minima, for example, but it also encodes the transition between this true vacuum of the Higgs to its smooth second order or crossover transition to its high temperature structure. Now, the effective potential itself is also a huge origin of uncertainty, because this is a thermal effect, this change here. These thermal effects are really prone to infrared sensitivity, and that is something I will mention in a little bit. At the same time, equilibrium is also a perfectly great approximation, for example, for the wall speed of the bubbles, which is something why equilibrium is also such an important sector to look at in these computations. Now, how large are these uncertainties that I've just mentioned? And they can be enormous. And for that, we can look at this plot where we plot the frequency against the energy density of the gravitational waves. And we can see that the peak frequency can be between 100 to 1 million in uncertainty. And if we now overlay the integrated laser sensitivity, we can see that in order to detect something here, we would have to really understand this band of uncertainty extremely well. The root of this uncertainty really comes from the fact that small uncertainties early on, for example, in the equilibrium, for example, here for the critical or the transition temperature, can propagate very far in the pipeline of the gravitational wave background, which means that if that has a very small uncertainty, it can become very large in the final convolution of all the errors. And this is not just entirely the case for the standard model. It can happen here for the standard model effective theory, but also for other models. And we've seen this for all the models that we looked at so far, that the uncertainties are always these huge bands, which are approximately 4 orders of magnitude. And that is extremely unsettling for something that we need to know at a sub% precision eventually. So for that, we can go further and think about a framework that can actually achieve this kind of precision. And the answer to that is using dimension reduction, which is an effective field theory framework for high temperature regimes. But first, we need to understand if we can even use perturbation theory for the computations that we do. So we can go back again and look at effective potential. And that is composed again of the tree-level bit and the thermal fluctuations. Now we learned that the thermal fluctuations need to be at least as large as the tree-level bit in order to modify the vacuum structure in a way that it eventually changes the phase. And for that, we can look at these ratios, the thermal fluctuations over the tree-level contributions, and that needs to be of order unity. So either you're strongly coupled, then you're out of the discussion that we are having here, namely using perturbation theory, or you exhibit a scale hierarchy between the fluctuation scale and the scale of the tree level. And that is exactly what we are going to use, these scale hierarchies, and because this is one of the key prerequisites in order to use effective field theory, and I will use that as an argument later on. Now, for computing equilibrium thermodynamic parameters, we can use the imaginary time formalism. This formalism is extremely practical because it allows for computing statistical expectation values by identifying the density operator with the time evolution operator, which means that now and time evolution is in fact something that is mathematically well understood in terms of the path integral. So now what happens is that the partition function itself can be expressed as a path integral in a finite temporal extent, because the expectation value of a statistical quantity goes via the trace. So that trace is reflected via this finite temporal extent, and that extent is 1 over the temperature. Now, depending if you're a boson or a fermion, it's either an antiperiodic or a periodic boundary condition. Since the extent is also finite, modes are quantized. And you end up with a set of different modes, which are called Matsubara modes or Matsubara frequencies that are even valued or odd valued depending on the particle that you're at. And as it happens then that for the bosons, you have this identically vanishing mass or frequency, which is this 0 Matsubara mode. And this mode is in fact related to all the infrared uncertainties that we will encounter in the future of this talk. Now, if particles really propagate through a thermal medium, they experience collective effects. One of these collective effects is that, for example, what used to be a weakly coupled particle has now a different effective expansion parameter, namely g squared times the distribution functions for bosons or fermions. So for bosons, what happens is that at high temperature, this effective expansion parameter is g squared times t over the energy scale. Now, there are now different energy scales that are entirely non-perturbative. For example, this scale, this g squared times t ultrasoft scale. But these are not the modes that contribute to the dynamics of the phase transition, the electroweak phase transition, for example. So these are entirely non-perturbative modes. Okay, we know that, and this has been known since a long time, which goes under the name of the Linde problem. However, there are still sectors that are fully perturbative, namely the G3 scale, and that is entirely the scale that relates to the symmetry breaking of, for example, the electroweak sector. And that is exactly what I discussed before. These are the prerequisites that we need, namely a scale hierarchy in the theory, because that will allow to use perturbation theory in the first place. This is exactly what I mentioned before. We need a hierarchy of scales here. The corresponding effective theory framework for that is called dimension reduction. And why it's called like that is simple, because all the non-zero Matsubara modes lived in the temporal direction of the theory. So we can integrate them out because they're all heavy, because they're all of the scale pi times t. Now, the effective theory is entirely three-dimensional, which is also logical because it's an equilibrium. Temperature, time dependence should not be as important as, for example, the temperature in this case. Now, how this construction actually works in practice is already implemented. And we did that with our software package DRalgo. And DRalgo does exactly that. It computes from the four-dimensional Lagrangian its three-dimensional effective Lagrangian at next to leading order, together with the beta functions and also the two-loop effective potential in 3 dimensions. But by going for a step of different diagrammatic operations, namely from the generation of Feynman rules to the use of integration by parts identities, which is all state-of-the-art at zero temperature, but also at finite temperature. Now, the strategy is now the following. We have a different strategy, namely using not the standard path by going from four-dimensional Lagrangian using a infrared sensitive resummation framework to a four-dimensional effective potential and then computing the thermodynamics. That is not the path we're taking. We're taking the path by the effective theory using dimension reduction, which as an EFT framework is an infrared safe step, and one can then compute from the corresponding 3D effective Lagrangian the three-dimensional effective potential, and from there the thermodynamics of the theory. Critical temperature, latent heat, strength of the transition. That's all encoded here. Now, how can we even go to higher precision? And for that, we can look again at the effective potential, and especially at its critical temperature, because there the mass of the Higgs changes sign, so which means that the quadratic part of the effective potential needs to change sign. For that to happen, the thermal effects will now push this whole quantity here through zero, which means that at different scales, this quantity will vanish. Or in other words, these different scales are generated dynamically, because first that quantity will go through zero at the soft scale, then at the super soft scale, and eventually at the ultra soft scale, and that is entirely non-perturbative. But for our discussion and for the discussion of using perturbation theory, only these first two steps are really relevant because they are first generated dynamically and they give all the information about the critical temperature and where the phase transition eventually will occur. Now, this can happen for standard phase transitions, for example, one-step transitions between in the Higgs phase, for example, here. But this can also happen for multi-step transitions. In case of two scalars, you can first break the symmetry into the one scalar direction and then later into the true vacuum of the Higgs. Now, let's understand a little bit better the structure of why it matters to get this effective potential correctly resummed. So as at zero temperature, the effective potential is a sum of endpoint functions. By executing that sum, you end up with a logarithm same as a zero temperature, but now with this thermal sum. Here you can now split the whole expression into something that is called the Coleman-Weinberg zero temperature piece and something that's called the temperature-dependent thermal function. But you can also do a different split, namely into the soft piece and to the hard piece. And this is exactly, these are the same scales that I've introduced before. This is really the scale related to the Matsubara zero mode, and this is the scale related to the non-zero Matsubara modes. Now let's compare RG improvement at zero and at finite temperature. And this will really give rise to what the true difference between the two regimes is. Now, if I am at zero temperature, the effective potential gets contributions at G level, and that from the Coleman-Weinberg piece at G to the 4. G to the 4 is where I want to go here. Now I can run this tree-level piece via the one-loop beta functions, and I arrive at RG improvement. So this is RG invariant. At finite temperature, the picture is entirely different. I again start, however, at G squared, get a G cubed contribution from the soft scale, so I get this non-analytic G dependence, but also have the hard contribution, which scales at G squared T squared, plus this G to the 4, which is the same as here. Now again, I run lower orders with the one-loop beta function, which means this G squared goes together with this G4. This G cubed goes at G5, so it's higher order than we want to actually compute, but this G squared times T squared will go at G4 T squared. Now, where do I get that contribution from? Naively, from nowhere, but as we know, I have to resum to the corresponding order, which means in order to achieve a G4 RG improvement, I need to have a two-loop thermal resummation also for the thermal masses. which means if I include those thermal masses at 2-loop order into the 1-loop effective potential, the 3-level effective potential, I arrive at the corresponding terms, which are G4 T squared, and they scale at the same order as this 3-level hard contribution. And this is exactly the problem. What used to be a 1-loop computation at 0 temperature is now a 2-loop computation at finite temperature. Okay, but I can push to higher orders, and really there's no limit technically speaking, but okay, there are some technical limitations. What you can do is go to 2-loop level, which is what we did in DRalgo. So you can compute the corresponding 2-loop vacuum bubbles of the effective potential, but you can also go to higher orders, which is then the 3-loop computation, which is something that is for the future, and which is something that will eventually also be featured in DRalgo. And as at the last step, I want to comment on what is the perfect minimal scheme in order to reconcile gauge invariance and resummation. As I said before, you determine the 3-dimensional effective potential at next to leading order, done by DRalgo. You compute the effective potential in 3 dimensions in the corresponding 3D effective theory at 1-loop order, which is the minimal version, but also you can go to higher loop orders and eventually determine all the thermodynamics by computing, for example, the condensates or the latent heat. And this we can now see particularly by increasing the accuracy to G to the 4, for example, in a complex singlet extension of the standard model. So basically what happens, I extend the standard model with a complex singlet that it has now a real contribution, but also a complex contribution. And I pick a specific benchmark and start from there. And what happens is now that I can look at the critical temperature or the latent heat. And in any perturbative computation, what should be the case is that its dependence on the RG scale should be as low as possible, because ideally this line would eventually be just flat. But okay, if I just use the 1-loop dimensional reduction, namely the 1-loop thermal masses, I will have a large scale dependence, and that is exactly what I don't want. Only if I include the 2-loop thermally resummed masses, eventually I push this line down and it becomes more flat and flat. And this is exactly why going to higher loop orders in the dimensional reduction and in the EFT is what we need. And the same behavior can be seen in the latent heat as well. Now this is where I leave you, by reiterating the point that effective field theories are an important tool to understand beyond the standard model theories in their stochastic gravitational wave background at unprecedented precision. There are a lot of features that can be used in that context, for example, universality, but also applying them, for example, to supercooled phase transitions eventually.